So let's look at the molecule formaldehyde. Now, formaldehyde, the carbon, my central atom, has three groups, right? So thinking about our scheme of S, P, 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 D, D, like that. Right, it's three groups. It'll be an Sp2 hybrid because I only need a total of three orbitals to accommodate my three groups. And so I'll recombine two of the p orbitals and the s orbital. The hybridized orbital is partway between in energy. It's a little bit closer to the 2p than the 2s, and then because there's two of them, right? And then I have this one unhybridized orbital. So what's going to happen is the carbon, right, is going to form sigma bonds with a hydrogen. Now remember, the carbon has the four valence electrons in it, so we don't have them drawn here, but it would be like this. Now that I have it hybridized, it's going to be like this. And then I'm going to promote one electron up to here, and I'll explain why that is in a little bit. But what we have is three unpaired electrons here. So two of them can be used to bond with hydrogens, because remember, the hydrogen has the 1s and has one electron in it, and so they'll pair. And there's another hydrogen, so it will pair like that. And then it's going to leave two orbitals in order to bond with the carbon to the oxygen. And you'll notice the carbon-oxygen is a double bond, right? Each of these electrons will contribute towards the double bond. So let's take a closer look at what's going on in terms of the shape of the molecule and the types of bonds that are being formed. So when I'm just looking at the carbon and oxygen, so let's say this is a carbon and this is the oxygen, this is the carbon and this is the oxygen, like this. What can happen is I can have a bond that occurs on the bond axis, right? But then I have another p orbital, and this orbital is actually representing this orbital here. So if I'm going to form two bonds between two atoms, then one bond can use an orbital that lines up on the bond axis, and that gives me a sigma bond. But the other one, because remember the p orbitals have to be 90 degrees to each other, well, that one has to form perpendicular to the bond axis. And this is what I was talking about before. One forms on the bond axis, one forms perpendicular. It's perpendicular because it has to be, because the way the atomic orbitals are derived, has to be 90 degrees to this orbital. Now, in the example we're doing here, what's going on is I have a hybrid orbital that's here. So this is an sp, that's going to, sp2. It's going to form a sigma bond with the oxygen. And as it turns out, all hybrid orbitals are used for forming sigma bonds, and unhybridized orbitals are used for forming pi bonds. So let me go back to the sp2 hybridization scheme. And this is what it looks like. I have an s and two p orbitals, and when they recombine, what I end up getting is three hybrid orbitals pointing at the corners of a triangle, which gives me my 120 degree bond angle. So this is my 120 here. But you notice what happened is when I combine these three orbitals, all of this recombination takes place in a single plane. That's why the geometry of the final product is trigonal planar. But the thing that's not shown here, and what's important for a discussion of pi bonds, is that there's actually an orbital that's sticking out like this. That's not being used. That's the unhybridized orbital that's shown here, not being involved in the bonding until we get to the formation of the pi bond. So on this diagram, I would have all of this material in one plane, but then if I was looking at it, there would be a top of a p orbital right here. If I was drawing it from the side, it would look something like this. Here's an orbital, there's an orbital, there's an orbital, like that. So that's all in one plane. It's not a very good drawing of something in a plane. But then there's this p orbital that sticks out on the top and the bottom, unhybridized and perpendicular to the plane of the other orbitals now. So when that bond forms, this forms the pi bond because it is, like I was saying, it's formed perpendicular to the bond axis. This is my bond axis, right? And perpendicular just means it's at 90 degrees. So it's 90 degrees to the bond axis. That the orbitals that form it are 90 degrees to the bond axis. So now let's take a look at the orbitals in formaldehyde and the types of bonds that it's forming. I have an Sp2 hybrid orbital on a carbon and a hydrogen s orbital. That forms this sigma bond, so this is designated as a sigma bond. And then I have an Sp2 hybridized orbital on the carbon. Remember, there's 3 of these that we made, forming a sigma bond with a p orbital on the oxygen, so that's this guy here. And then there's an unhybridized p orbital sticking out like this, and like this, and like this, and like this on those 2 atoms, and that forms the pi bond, right, between the 2, and that creates what's called, right, a double bond. So in the sort of valence bond theory, what we find is that a double bond, it's composed of a sigma plus a pi bond. And if we do a triple bond, it'll actually be a sigma bond plus 2 pi bonds. Now, the pi bond overlap, even though they show this big, thick connection top and bottom, is actually not that good. Remember, these orbitals, at best, have a shape that looks like this, right? And a shape that looks like this. They're just trying to emphasize the connection in the diagram. But in reality, the pi bond interaction is much weaker than the sigma bond interaction. So one of the things that we saw when we were looking at bond energies is that a double bond isn't twice as strong as a single bond. And the reason for that is, according to valence bond theory, while the sigma bond has good orbital overlap, the pi bond has much weaker orbital overlap because they're not head-to-head is the way we say it. This is a head-to-head interaction. This is a side-to-side, side-to-side interaction. Okay, so this bond is described as a sigma bond between the carbon sp2 and the oxygen p, and then this bond is described as a pi bond between the carbon p orbital and the oxygen p orbital. And as I said, the central atom always makes sigma bonds with hybrid orbitals and pi bonds with unhybridized orbitals. So one of the things that Lewis theory and Vesper theory can't do is explain why some bonds are able to rotate between 2 ends of a molecule. So if you look at a molecule like methane, methane is just CH3CH3. So it looks something like this. At room temperature, this bond in the middle rotates about 1,000,000 times a second. So it's a very high rotation rate. And that's just based on thermal energy, right? How much energy it has at room temperature. Now, there's no good explanation for why in Vesper theory or Lewis theory that a sigma bond rotates so fast, but a double bond doesn't rotate at all. So if I had a molecule like this, for example, right, there's no rotation between this side of the molecule and this side. Now they can both rotate together, and they rotate fairly quickly, but one side doesn't get to rotate without the other side rotating. And it turns out the origins of this has to do with sigma bonding and pi bonding. So I'm going to go to this slide real quick and show you what a sigma bond looks like again. So this is for dichloroethane, right? And we have 2 chlorines here, and ethane is the CH2 carbon hydrocarbon. This bond gets to rotate freely because in a sigma bond, the overlap doesn't really change as the bond rotates. So the 2 ends of the molecule can stay together, and the opposite ends get to rotate. I mean, they get to rotate, sorry. The bond gets to stay together, but the molecule gets to rotate around that bond. Now, if you look at this molecule, which is similar to the one I drew here with chlorines on either side of the carbon, right? These are opposite of each other. I have a molecule like this with the chlorines on the same side. It turns out there's zero rotation in this bond at room temperature. And the reason there's no rotation is because even though the sigma bond that creates the double bond can rotate, the pi bond doesn't get to rotate. If you try to turn this end of the molecule 90 degrees, you end up breaking the bond. Now, to break a bond, as we've talked about before, requires the input of energy. So it is possible to get this to rotate, but you can only do it if you add the energy, and that's not going to happen without any like light input or heat energy input. And so at room temperature, typically this bond is stationary and doesn't rotate. So what it says here is that sigma bonds can rotate because the overlap is on the bond axis, and rotation doesn't change the degree of overlap or does not break the bond. On the other hand, the pi bond overlaps are above and below the bond axis, and so when you rotate it, you end up breaking the bond. If you do get a bond like that to rotate, you have to add energy to it. So a double bond can rotate, but it can only do it if you break the pi bond and leave the sigma bond intact. So it turns out this non-rotation, this prohibition of rotation between the ends of the double bond means that you can actually have two different molecules. There's cis 1,2-dichloroethane and ethene, and trans 1,2-dichloroethene. Ethene, the ENE, indicates there's a double bond here. So these are actually two different molecules that can be isolated from each other that have distinct properties. For example, dichloroethene in the cis conformation has a net dipole, which is the sum of the dipoles of the two ends of the molecule, which points like this. So we have vectors for these, or think about the rubber band idea again. We have rubber bands pulling in those directions, so that means there's a net dipole. The two carbons now will be pulled towards this direction. On the other hand, when you look at trans 1,2-dichloroethene, there's a dipole that pulls this way, but there's also a dipole pulling this way of equal strength. And the result is this molecule is generally nonpolar. But again, because there's a pi bond there, these don't freely interchange with each other, and they're easy to isolate from a mixture because of the differences of their properties. I also wanted to point out that what I had mentioned before is that a sigma bond is stronger than a pi bond. So here are the bond energies for a CC single bond, 347 kilojoules per mole, and a CC double bond, 611 kilojoules per mole. Now, if this had been if it had been true that a double bond was twice the strength of a single bond, we would have expected the bond strength to be like twice this, right? And that would be 694 kilojoules per mole, when it's only like 611. So if you're comparing like bond strengths, one of the other things that we can do, besides looking at that it's not double the strength of a single bond, is we can just calculate the difference between these two. So we know that this is a sigma bond, and this is a sigma plus pi bond. And if we just subtract those two numbers, what we end up is a difference that says the pi bond has an energy of about 264 kilojoules. That's sort of a ballpark thing. It's not going to be exactly that every time, but you'll notice 264 is significantly less than 347. And that happens because of the poor overlap between the p orbitals that are in the pi bonds being side by side.